Okay, in this video we're going to do a quick overview of colligative properties of solutions. So when you think about colligative properties, think about this. When we have a bad snowstorm or we're threatened with icing, we can go from this to a situation where there's no snow or ice on the roads, and we do that by putting salt down. And that's all based on colligative properties. So colligative properties are defined as those that depend only on the number of solute particles and not on their identity. So the properties that are affected by the number of solute particles are vapor pressure, and vapor pressure gets lowered. If you can remember these terms, it will help you remember which way things go. Vapor pressure gets lowered, boiling point gets elevated, and freezing point gets depressed. If you're going to do problems with colligative properties, you need to learn a new term for concentration, which is molality as opposed to molarity. We replace the R with an L, and this is a small m, whereas molarity is a capital M. And the reason molality is used is molality is constant, does not change with the temperature. Molarity can change with temperature, because if you go from a cold day to a hot day with the same solution, the liquid can actually expand by a little bit. So if you look at what happens to the volume of the solution, on a hot day, you actually end up with a little lower molarity than you would on a cold day. So molality takes this into account. Molality is constant with temperature changes. So they're very similar formulas. You know molarity is moles of solute per liter of solution, whereas molality is the moles of solute over the kilograms of solvent. So remember, for water, this is water, at 25 degrees C, 1 gram is 1 milliliter. So 1 kilogram is equal to 1 liter. Okay, so if you're at 25 degrees C, your liters and your kilograms of water will be exactly the same. So molarity and molality, the values for those are very similar. Okay, so let's talk about what actually happens. Why are boiling points raised and freezing points lowered? It's all about what happens with the solute in water. It's going to be attracted to the water molecules, which prevents the water molecules from being able to do the things that it does during boiling or freezing. So if let's look at the bottom diagram. If I were boiling water and I have particles pulling on that water, it's going to be harder for them to escape. Okay. If I have something that's frozen and I heat it up, it is going to be easier for those water particles to separate and to melt than it will be if the particles of water are attached to the solute. The other property that's affected is vapor pressure. This is very much like boiling. If you have a bunch of solute particles, you're going to have fewer that are holding that liquid in place. Fewer of them are going to be escaping. So the vapor pressure is lowered. So it's all about the number of particles, not the actual composition of those particles. So if I put sodium chloride in water, it breaks up into Na plus and Cl minus. So if I have 1 molal of that, then I have 1 molal of Na plus and 1 molal of Cl minus for 2 molals of particles. Same thing happens here. I end up with 1 Ca2 plus and 2 Cl minuses. So for 1 molal of this, I get 3 molals of particles. Here I get 3 plus 2, or 5 molals of ions. The difference is, for ionic compounds, they break up into ions. Molecules, things covalently bonded, do not break apart, do not ionize. So I only end up with 1 molal. So anything, it could be an alcohol or any covalent compound is not going to break apart. So I will end up with 1 mole of that. So ionic compounds are much better at affecting those properties. On a lot of the tests, you won't be, you'll be asked qualitatively, so they will ask you something like, what's going to have a higher boiling point, 1 mole calcium chloride or 1 mole sodium chloride? And the answer will be calcium chloride because there's more particles. But if you are asked to calculate, here is the equation that you'd use. So the change in temperature at boiling is the molality times some constant which has to be provided for you. So here's the value for water. And I is the number of particles. So if I have NaCl, I is 2. If I have aluminum oxide, my, Al2O3, my I is going to be 5 because it breaks up into 5 ions. Freezing point depression is basically the same temperature change, but my K value is a little bit different. So M is the molality, and I is the number of particles that the solute dissociates into. So this is the change in temperature at boiling and freezing. So let's take a look at a specific problem. So this is a typical kind of a question you might get. What's more effective at lowering the freezing temperature? And the answer is going to be calcium chloride because it's twice as many particles. So if I had to find the new freezing point of 3 mole sodium chloride, what I know is the change in temperature is molarity times the K sub F times I. This is just a freezing constant. Okay, so my molality is 3, my K is 1.86, and my I, or number of particles, is going to be 2, which is what the sodium chloride dissociates into. And if I multiply that out, I get 11.16 degrees. Now this is the change in temperature. Water normally freezes at 0 degrees C. And because I have freezing point lowering, that means it's going to lower the freezing temperature. So this is the change in temperature. So this is the change in temperature. So my new freezing point is minus 11.16 degrees C. Same problem here. I have boiling point elevation in this case. So if I take the change in temperature, it's going to equal my molality, which is 3. My constant for the boiling point of water is 0.51. It's still going to break up into 2 particles. I multiply that out and I get 3.06 degrees C. So that's the change in temperature at boiling. But the new boiling point is going to be the standard boiling point, 100 degrees C. I'm going to elevate that by 3.06 degrees C, and I get 103.06 degrees C. Okay, that's going to do it.